Okay, great. So welcome everybody to our seminar series of the Erlangen AI Hub for Mathematical Foundations of Artificial Intelligence. Today we have speaker Alessandro Micheli, who's going to be giving our next talk. So Alessandro completed his PhD at Imperial College London in the Mathematics of Random Systems CDT. He's currently a postdoc in mathematics at Imperial College and also in machine learning and public health at the University of Copenhagen. Alessandro is interested in probabilistic and geometric machine learning, as well as computational algebra and geometry. And today he will be speaking about a new project on Riemannian Neural Optimal Transport, which is joint work with UT Cal, who's based at KTH Sweden. Myself was very fortunate to get to work alongside Alessandro on this project, and Samir Batz, who's based at the University of Copenhagen. And this talk covers generative AI, optimal transport, and Riemannian geometry. There's also a QR code to the linking to the paper if you're interested. But otherwise, we are very welcome to have Alessandro speak with us, speak this morning. And Alessandro, I'll let you take it away.
Hi, Anthony. Thank you very much. Yeah, today I'm going to talk about Riemannian Neural Optimal Transport. This is our most recent work, and it's a framework about generative modeling on a Riemannian manifold using a combination of neural network and optimal transport techniques. So let's start with some motivation. So the idea is that we would like to leverage optimal transport for generative modeling. And this can be done because optimal transport allows to learn a transformation that pushes some reference distribution. Let's say symbol reference distribution, in the sense that we can easily sample from that. So it could be a Gaussian, for example, to some data distribution that we observe, and while minimizing some transport costs. These are existing results which are very well known. Kantorovich, for example, gave a studied this problem, but also Villani is like world famous for addressing problems in this space. In the Euclidean setting with quadratic costs, the optimal transport problem has a well-known solution, which is given by the optimal Monge map, which can be written as the gradient of some convex potential U. This is a result from Brenier, which is relatively famous in the field. And the idea of neural optimal transport is to learn neural network parameterizations, either of the map or the potential, which can be trained by optimizing the optimal transport objective. So this is a well-studied problem in machine learning. And the main motivation for this is that it gives a way to perform amortized sampling. This means in practice that if I draw a sample from the reference distribution, then by passing it through the neural network, I'm able to generate a sample from the data distribution immediately without solving again the transport problem. So far, we discussed about optimal transport on Euclidean settings, but many data sets in real life, especially in scientific problems, live on Riemannian manifolds. So this could be spheres, tori. This has applications in protein modeling, geology, robotics. And there exists optimal transport methods for the work on manifold, and the optimal transport map is learned through some discretization. So one of this example is Riemannian convex potential maps, RCPMs. This is a work of Cohen and collaborators, and they learn C-concave potentials, which parameterize the optimal transport map by looking at finally many discrete sites on which this potential is anchored. So the one of our first results for this work is that we show that discrete optimal transport method or discrete method that provide discrete approximation to the optimal transport map. They face a curse of dimensionality problem, which means that to achieve a certain accuracy, the number of parameters has to grow exponentially in the manifold dimension. This is the book definition of, if you want, curse of dimensionality, effectively. So we start with this negative result for discrete paradigms, but this then does not exclude the possibility that actually one can recover favorable rates if one finds a continuous parameterization for optimal transport of manifolds. And in fact, some results, as we will see, in geometric deep learning, they show that it is possible to avoid this dimension-driven blow-up if one assumes further structure on the functions, for example, to learn. So the missing piece in this framework is basically a neural optimal transport framework that can learn the transport map intrinsically on the manifold with theoretical guarantees beyond the Euclidean setting, which can actually avoid this curse of dimensionality results problems. And this is what we introduced in our paper, which is we call Riemannian Neural Optimal Transport, or RNOT. We learn a continuous parameterization of potential on the manifold, so without requiring any discretization. And we enforce the optimal transport structure, which is expressed through C concavity by construction, by taking a class of C-transform functions. And this, once this has been defined, then one can recover optimal transport maps by taking the exponential of the gradient. This is a standard result, which we will see. And we provide universality results, so universal approximation results, as well as we show that this method, under certain conditions, supports uncursed approximation rates, polynomial, therefore, in the manifold dimension and not exponential. We also show empirically that this method has better scalability and competitive performance with existing methods. So like the roadmap for our discussion today is the following. So I'll start with some background on optimal transport of manifold and geometric deep learning. Then I'll show our first result, which is a negative result, where we will see that discrete approximations of optimal transport maps suffer in a dimension. And then we will introduce our framework, which is Riemannian Neural Optimal Transport. And from that, we will show that this framework supports uncursed rates for learning. Then we will verify our methodology in the experimental setting and discuss some limitation of future work. So let's start with the background. So I'll set up some notation and common assumptions here. So M is a connected, compact, smooth p-dimensional Riemannian manifold, on which we can define a geodesic distance d, and p is the set of Borel probability measure, and the volume here is the Riemannian volume measure. So the assumption on the manifold effectively are the one we inherit from the existing literature of optimal transport, and they're necessary to define actually optimal transport maps on manifold. So on manifolds, as we have seen, basically in the Euclidean setting, the transport map can be expressed as a gradient of a convex function. So the equivalent setup here is to look at C concave function and C transforms. So for a cost function C and a function psi, we define the C transform as in equation 1. And we say that a function phi is called C concave if it can be written as the C transform of some other function. It is possible to show that on a compact manifold M, if the cost is regular enough, then the C transforms are continuous. And so the C concave potentials, which are what we'll look at, are also continuous. And this is already verified in the context of square cost, as we will see now. So this plays the equivalent role of a convex potential in the Euclidean optimal transport setting. So the key problem that we are interested in looking at in the context of optimal transport is the Monge problem. So we have some source measure mu that we would like to transport to some target measure nu through some measurable map T. And we would like to find this T by minimization of the cost in equation 2. As I mentioned, we take the canonical case of square distance cost. And if we do so, McCann showed that under certain assumptions, the key assumption is that mu is the absolutely continuous with respect to the volume measure on the manifold. Then there exists an essentially unique optimal transport map. And this optimal transport map is induced by a C-concave potential phi and satisfies equation 3. So it can be recovered through the Riemannian exponential of the gradient of such potential. So now that we discuss optimal transport, I'll give a brief overview of some results on geometric deep learning, which are key to show the universal approximation properties of our framework. So in geometric deep learning, what we are interested in effectively is to learn functions on manifolds. And a common strategy to do this is to reduce the learning on manifold to learning on some Euclidean space through some feature map, such that we can leverage existing results on the Euclidean space on the manifold. So in general, people look at what is called uniform convergence on compact sets for approximation. So if you have a sequence of function fk, we say they converge in UCC if and only if for every compact subset of a topological space X, the supreme norm on this compact goes to 0. Since we take M to be compact, then basically UCC convergence is equivalent to the uniform convergence with the following norm. So now let's consider a class of function f, which we take to be dense with respect to UCC convergence. In this case, can be given, for example, by neural networks, since we know that neural networks have universal approximation properties. And we define what we call like a pullback class of some feature map. And this is just given by the composition of the feature map with functions from this dense subset of F. And the approximation power of this pullback class depends on the feature of map, especially now this feature map preserves information. So the key property is that the feature map should be continuous and injective. Since this is key, so we can distinguish points on the manifold effectively. Kratsios and Bilokopitov show the following principle, which is really interesting. So if F is some universal class on R, so basically that has this universal approximation properties, and phi is a feature map which is continuous and injective, then the pullback class is universal on the manifold, which means that we can learn functions, continuous function on the manifold. But if phi is not injective, then this universality can actually fail. So there exists some continuous functions which can never be approximated by any such construction. So far we talked abstractly about this feature map, but we should also consider like how this can be implemented in practice. And the way to do so is through an embedding which is constructed through some distance to landmark. So we have a set of landmarks xi, which we take to be a maximally delta separate subset of M. So it's a subset of the manifold, which since M is compact is going to be finite, which is sufficiently spread. So with this subset, we define the feature map phi by just taking, for every evaluation point, we just take the distance from each landmark. And this will constitute basically our feature map. And there's an existing result of Gromov that shows that for sufficiently small delta, then this type of feature map is continuous and injective. So it constitutes effectively, it satisfies the assumptions that we were just discussed. Finally, brief notes on existing results on bringing on the curse of dimensionality on manifold. So the Kratsios and Papon were the first to show that it is possible to obtain approximation results of manifold without exponential dependence on the dimension. But their setting is kind of peculiar because they look at how these approximation rates and results they focus on a fixed data set, which is can be finite or infinite, but it's still a subset of the manifold. So the approximation is not uniform on the manifold itself, which is the standard way of actually defining approximations of functions on spaces. But they show that if the target function f is sufficiently regular, then one can achieve absolute accurate approximation on the data set, on this data set, with polynomial complexity instead of exponential. So it is possible in some way to actually recover uncursed rates on the manifold if one assumes sufficient regularity on the function. Nevertheless, this does not really transfer to a fully optimal transport result. And the main reason for this is that their result is fixed. It's on a fixed data set of finite or even infinite. It wouldn't be the same. Would be the same. So while we would for this kind of results, we will need a uniform uniform approximation result on the entire manifold, which is what we will obtain. So now, like, we start with the first results of our paper, which is why discrete optimal transport methods suffer in high dimension. And this is a negative result, but it will give us the right direction to look at for our framework. So again, just to recall, we study optimal transport on a compact p-dimensional Riemannian manifold, and we look at these quadratic costs. So our discussion will cover discretization in a very general sense. So either explicitly, so through meshes or landmarks, grids, or implicitly. So the methods that at some stage will introduce some discretization, like, for example, Riemannian convex potential map. So our main claim is that any finite support transport map incurs a curse of dimensionality barrier, which means that for to obtain a fixed accuracy, one will require exponentially many discretization point or support point in the manifold dimension. So one example of this is the example of Riemannian convex potential map, which as we will show, they also fall within this category of discrete output maps, so they incur the same barrier. So to be a bit more rigorous about this discussion, so let's fix one source measure mu and a target measure nu, and let T star be the essentially unique optimal transport map pushing mu to nu for the quadratic cost. Here, of course, necessarily we need to assume that, as we will see, mu is absolutely continuous with respect to the volume measure. And we measure the approximation error through some root mean square error defined on the manifold. So we're given some the source measure, we can actually compute the quality of our approximation on the manifold looking at this quantity, which is the equivalent of the Euclidean, if you want, definition of the root mean square error. So we need to we introduce a class which is sufficiently in general to cover most of the cases for discrete optimal transport parameterization, and we basically look at the transport maps that output to finally many locations. So we define this dm mu, which is a map, a measurable map, such that the push forward. This is a class of measurable maps such that the push forward is supported on most endpoints. So the approximation that it provides of the target measure has a finite number of atoms. So this is equivalent to say that for any given point in the manifold, the image of this point under the map T will be contained in a finite subset. So it will be one of finitely many points out of which one can select. So our first result shows the following cursor dimensional barrier. So let's assume that mu and nu are both absolutely continuous with respect to the volume measure. So one approximate the optimal transport map with a discrete output map from the set we defined before. This forces what is called an M-atomic approximation. So the absolutely continuous measure is actually approximated by discrete measure with M atoms. This technique or approach is called quantization, in fact. And our result shows the following cursor dimensionality barrier. So there exists some constant which depends on the geometry of the manifold, on the on the target measure, such that for all m, the root mean square error satisfies the following bound. So what does this mean in practice? Is that for any discrete approximation, discrete output map T, if one wants to achieve a root mean square error which is smaller than delta, then we'll need a finite number of points which satisfies this inequality. So effectively, this number of points grows exponentially in the dimension of the manifold, which is the definition of cursor dimensionality. So this result is really interesting actually, because it is structural. It doesn't depend on the algorithm that you use to fit your discrete approximation. It does not depend on the optimization procedure. The only real assumption is that we really care about is that the approximating map as a uses a finite pushes like the source measure to a finite measure. So this effectively covers most of the cases of discretization-based Riemannian optimal transport methods, which incur exactly this cursor dimensionality result. So this is also relevant for Riemannian convex potential maps, which is effectively the leading method for computational optimal transport of manifolds. In this case, Cohen and collaborators, they introduced what are called discrete C-concave potentials. So the C transform of the potential map is actually approximated by a minimum over a finite set of sites of size m, so m size, and they show that this class is actually dense in the class of C-concave potential, so they do satisfy the correct universal approximation properties, but when one actually implements this class, must choose a finite m, and such that the induced optimal transport map actually we show that takes value in a finite set of points, and therefore incurs exactly the same cursed approximation rates that are valid from the more general class of discrete output map. So this kind of justifies introducing a method which does not incur this cursed approximation rates. So the problem here, again, that we should focus on is that these methods are discrete, and from this discretization, we obtain some transport map, and therefore like the approximating target measure, which has finite support. So it is natural at this point to think of a optimal transport model, which is continuous, such that it doesn't really rely on discretization or discrete outputs, and also ideally should include the structure of optimal transport problem intrinsically in a way that we will see. And so this is what we'll show in our framework is RNOT. So we parameterize the transport potential phi through a neural network, and then define the map through the exponential, as it was shown like on the result from McCann. And this will give a manifold value, continuous generator, which was push approximating a target measure actually is not confined to finitely many points. So already by design, it will not suffer the same curse of dimensionality barrier that we just discussed. So to define our framework, let's introduce some notation. So we consider a class of, let's say, rich class of Euclidean function. What does this mean? In practice is that we take a class to be F, which is UCC dense, as we had previously defined. And let phi be a feature map. And to transfer this class to the manifold, we still consider this pullback set of functions, which are just given by the composition that we see here. These functions are indeed continuous, but they are not optimal transport potential yet. And to do so, we must, or at least candidate optimal transport potentials. To do so, we must introduce C concavity. So we define the class of C transform functions. So given some class G as obtained as a subset of continuous functions, then we define the class of C transform in the following manner. And so once we apply this definition to the fullback class, we can think of modeling optimal transport potential through this class here, such that basically C concavity is built in by construction. We are guaranteed that this function is going to be C transforms of something else. So our first result is a universal approximation result. So we must assume, of course, that the source measure is absolutely continuous with respect to the volume measure, and that we have quadratic costs for this. So are basically the assumption we inherit from McCann. We take F to be dense in the class of continuous function and the UCC topology, and we take the feature map to satisfy the assumption we had defined before, so to be continuous and injective. Then our result shows that there exists a sequence of C concave C transforms of the pullback class, which induces map TK such that they converge to the optimal transport map almost everywhere. And from that, it's easy to obtain that they also converge in probability under mu. So this class, we have just shown that it satisfies the desired universal approximation properties that we were looking for. So far, our discussion was framed in terms of a generic class of dense functions, but we are really interested in neural network instantiation of this setup. So let sigma be an activation function, which, for example, we can take to be a non-polynomial activation, and let this NM class be a UCC dense feed-forward class of neural networks, which again, since we assume that there are non-polynomial activation functions, then there's plenty of results that actually show that these have the necessary density properties we are looking for. And let also phi be this continuous injective feature map. Then within this framework, we define Riemannian neural optimal transport potential as the C transform of the pullback class of neural network functions. And from this, immediately we define the Riemannian neural optimal transport map through the exponential of the gradient. So this set of functions, we already guaranteed that they will satisfy the universal approximation property we discussed before. Now we'll show how this setup actually supports curse architectures which can break the curse of dimensionality. So we will show that we can approximate Cantor exponential and then the induced transport map with a complexity that grows only polynomially in the accuracy. So this is not the exponential blow up we were looking at before. and our proofs is kind of like divided in 3 steps. First, we effectively extend the result of Kratzios and his collaborators from a finite data set to actually a uniform convergence on the manifold with uncourse rate. And then from there, we further extend this result to optimal potential on the manifolds through the C transform. And then through a stability argument, we show that this applies directly to optimal transport map. So we have, from a technical detail, basically, we must restrict our discussion to Riemannian Neural Optimal Transport, to a Riemannian Neural Optimal Transport framework whose neural network architecture are given by feed-forward architectures with W number of parameters and L layers, and especially that they have non-affine piecewise linear activation functions. So this means basically ReLU or more broken ReLU into pieces, if you want. So the first step is that we show that if you have a sufficiently smooth function, psi here, then one can construct a pullback network that satisfies this uncourse rate. So we show that there exists some future map phi star and a neural network G, such that their composition achieves uncourse rate, which indeed scale polynomially in the accuracy. So already this extends the results of Kratzios that we discussed before to the entire manifold setting. In fact, notice that here we take the supremum norm, which is taken over the manifold instead of a finite set. And the idea is effectively analogous. We also must restrict our discussion to functions whose regularity varies with the manifold itself. From this result, then we can actually transfer the approximation rates also to the potential. So as we said, RNOT searches over the class of C transforms of pullback networks. In this case, specifically for this instantiation of feed-forward neural network class. So let psi star to be the optimal transport potential we would like to learn, and psi star to be its C transform, so it's pre-potential if you want. So if hat psi uniformly approximate psi star, then the same approximation transfer to the C transform, and therefore the same rates as step one, as the previous step, will transfer to the C transform, which means that in this way we obtain the same polynomial complexity rates of step one to the in the case also of the optimal transport potential. This is purely a result that depends on the Lipschitz property of the C transform function, actually. Finally, this result can also be transferred to transport maps. So the transport map, on top of being able, one could actually explain it through, express it to the exponential of the gradient. It can actually also be expressed to the the argmin of this polynomial minimization problem. And so if one looks at this carefully, can actually notice that can actually prove that a small change in the minimizer, which is induced by the change in the prepotential, actually is stable. So it doesn't blow up or unnecessarily complicates the transfer of complexity rates. So the result that we show is the following stability result. So there exists a subset of the manifold with full measure, so mu of omega equal 1, such that for every x in this subset, there are cx, which is a constant depending on x, and a parameter epsilon x, such that if the prepotential or psi here is approximated with sufficiently well, so smaller than epsilon uniformly, then point-wise, the approximation of the transport map that one can recover is also controlled by this parameter epsilon. And so what does this mean in practice? Is that if one now compose all the steps from step 1, 2, and 3, including this stability result, then our Riemannian Neural Optimal Transport framework, when it's initialized with the neural network architectures that we discussed before, with the non-affine piecewise linear activation function, one recover a framework that can learn continuous approximation, continuous manifold optimal transport map with polynomial complexity bounds on the number of parameters. And therefore, point-wise, it can avoid the discretization-induced explosion that we saw, that we just introduced at the beginning of this talk. So now we'll show some experimental results of this framework. So we compare RNOT against other manifold generative transport baselines. We look mostly at flows baseline or optimal transport methods. And so we look at 2 examples. So one is like, can this framework actually model some realistic manifold data? So this is a toy example on a continental drift. And then we look how this framework scales with the dimension, because clearly the key here is that this framework should have some nice dimensional scaling out of this discussion. So we use the distance to landmarks feature map that we discussed before, and this can be implemented in 2 ways. One is furthest point sampling, and one is like a random sampling. So this is how we choose the landmark, and we evaluate the performance through the KL divergence, ESS, and how much time it takes actually to run this method, the wall clock time. So in this case, so this is our first case study. This actually is really similar to what has been shown already by Cohen, who introduced Riemannian convex exponential maps. So we look at a transport problem on the sphere using paleogeographic reconstructions. Basically, we look at the distribution of terrestrial maps 150 million years ago, and we want to learn a transport map to the present-day mass distribution. And so this boils down to learning an amortized map T on this 2 sphere. We train our method with the furthest point sampling landmarks in this case. And so we can see that basically, as I will show now, the transported map matches the present, can match the present day mass distribution. It also gives, if you want, an interpretable way of how to map ancient locations, terrestrial locations, on to the current ones. So what we do here is that we look at the geodesic interpolation, as I will show now. So instead of like looking at the starting point and ending point, we look at a continuous parameterization, if you want, of this of the transport path. So the initial point will be the source point, and the final point will be the current mass location. So T is in some sense some time parameter. And we can see that in this example, we can actually recover some meaningful motions that is already well known in the literature of geoplates. So, for example, the regions near the Eurasia and North America boundary, they move in opposite direction. And our results are kind of qualitatively consistent with the known literature of plate separation. So specifically, so this is like it's a map of the Earth, as you can see, and the red points are the mass samples from the landmass distribution 150 million years ago, and the blue points are the locations, the current locations, and the here the pink points are the point push forward through the neural network parameterization we have learned. And on the final panel, we can observe the geodesic motion through the sphere. So as we've seen, like basically, we can recover the same current mass distribution and we can also, interpret the trajectories of how the points moved from one point from the initial location to the final one. Now we look at synthetic experiments on the n-dimensional sphere and n-dimensional torus. So we start first with some two-dimensional setup, and then we will look how the performance changes as the dimension increases. So for each manifold, we take a uniform distribution as the source distribution, and then as a target distribution, we take a wrapped normal, which is effectively the equivalent of a Gaussian distribution in the Euclidean setting. We take the target to be centered on specific points on the manifold, so as exactly as in the Euclidean setting, you need to set up some mean, for example, for a distribution. We compared this against the three leading, if you want, baselines among the class of transport maps and normalizing flows. So there's a Riemannian convex exponential map, Riemannian continuous normalizing flows, and Moser flows. So for the Riemannian convex exponential maps, which is in some sense the closest to our framework, because it actually comes with theoretical guarantees and tries to recover an optimal transport map, one actually must introduce a regularization parameter, and this regularization serves as a way to regularize the minimum and to make it less, if you want, sharp and more smooth. So smaller gamma will make the minimum closer, from the computation of the minimum closer to actually being a sharp minimum, and bring the method closer to a discrete regime, if you want. So this is just to show, this is our algorithm, and just a qualitative result. So on the first panel, we look at the source measure, both on the sphere on the top and on the bottom on the torus, two-dimensional torus. And on the second panel, on the B panel, we show the target measure. The third panel shows the transport geodesics. So from basically the path that the transport map takes from the source, from a sample of the source measure to the target measure. And finally, just the last plot is the push forward measure under the learned optimal transport map. As you can see, qualitatively, they look very similar. So then we look at quantitative results. So for RCPMs, in the case, so we choose the best parameter for RCPM, which happens to be when the model is the smoothest. So in that case, would be gamma equal to 1. And so in the case of a two-dimensional sphere, RCPM actually performs better than our method. So the results we report are mean plus confidence interval over 5 different runs and a clock time as well. So RCPM on the true sphere is faster and gives better results. But this is not really the focus of our work, as we will see. Our results still remain strong in the sense that we still achieve a low dimensional KL divergence. But for example, RNOT is just lower in this case because it has to run actually an iterative procedure to compute the implicit C transform. Now, if we turn to the two-dimensional torus, the RNOT actually has the best performance overall, as we can see. We obtain a much better match to the target distribution, and the existing normalizing flow methods actually perform much worse than our method. So this is the case of Riemannian continuous normalizing flow and Moser flows, for example. Now we will sweep the dimension. I will show that actually comparing to the RCPM case, our performance remains stable across dimension, while the performance of RCPMs, as predicted by the theory, degrades as p increases. As we said, as we will see, larger gamma makes RCPM smoother and therefore helps performance, but it still doesn't fix the dimensionality effect that we observe. And so I will show now results up to dimension 10, but in the appendix of the paper, we extend these results up to dimension 40. So these are our results. We measure the KL divergence on the y-axis, and on the x-axis we measure the dimension of the manifold. So there's two panels. Left is a p-dimensional sphere, right is a p-dimensional torus. So we have different runs of our CPNs with different choice of regularizations, and in red we present our method. So as we can see, especially as the RCPNs become more and more discrete, the performance degrade, while both in the setting of the sphere and the setting of the torus, while in our setup, it's pretty much stable. And therefore, we cannot outperform the existing methods. So we have run also an ablation analysis, and so there's two key conclusions from our ablation analysis. So first, having a smarter choice of landmarks certainly helps. So compared to choosing random landmarks, actually, if one takes furthest point sampling landmarks, this gives a better performance. And also, we have our algorithm relies on an iterative procedure. This is why it takes a bit longer to run compared to the existing methods. But actually, warm initialization for this iterative procedure, which is based on some exponential approximation, actually has a big impact on performance. So in a nutshell, our method is competitive and, as we've seen, frequently better than on key tasks, and has improved scalability compared to, for example, RCPNs, which has discretization. It's a discretization method, but it comes with a trade-off of longer running time due to this iterative procedure we use to complete the implicit C-transform minimization. So now we concluded some discussion and limitations of this method. So first, okay, just to recap, what did we establish? It's like this is the first theoretically grounded neural optimal transport framework on Riemannian manifolds. We started from negative results, which show that discrete approximations of optimal transport maps, they suffer a curse of dimensionality, which means in practice means that to achieve a certain accuracy one requires exponentially many parameters or support points to approximate the target measure. So our framework, Riemannian Neural Optimal Transport, circumvents this problem altogether just by considering a continuous approximation of the pre-potential, and then recovering potential through a construction via the C-transform, which enforces C-concavity, and then through this definition of the potential map, we can actually recover the approximating transport map through the exponential of the gradient. So in the setting of non-affine piecewise linear activation functions, we show that we obtain polynomial bounds in the accuracy on the number of parameter counts and depth of our neural network architecture. And we show this uniformly for potentials, and then we show how this transfers pointwise to on a full measure set to optimal transport map approximations. So we then look at we looked at the experimental results, and the results show that the leading method for learning optimal transport maps on manifolds degrades sharply as the dimension grows, while the Riemannian Neural Optimal Transport framework that we developed remained essentially flat on the dimension we tested. For the low dimensional case of 2 dimensions, our performance are competitive, and on the 2-dimensional torus are actually stronger. And also we have seen that based on the continental drift case, this framework gives rise to an interpolate way of looking at transport trajectories. So let's we conclude with some limitation and future direction. So in this setting, we just look at the compact manifolds, for example. This covers spheres, tori, but there's certainly many manifolds which are not compact by definition. And our approximation rate relies on regularity, smoothness of prepotential. So it's not cannot be stated in the most general setting. And computationally, like our framework is the training cost is dominated by an iterative minimization, which is required to compute to evaluate the C transform. So the idea is that for future work, one could look at extending this to theoretically to other settings, and also to try to accelerate the inner solve, which is the main computational bottleneck. So what we've shown today is basically that the Riemannian Neural Optimal Transport, the framework we developed, is a scalable, amortized optimal transport method on manifold, and which also theoretically enjoys dimension-friendly guarantees, which we also have proven verified in some sense in the experiments. This is all. Thank you for listening. I'll take any question if there is any.
Thank you very much for the nice talk, Alessandro. Are there any questions from anybody?